Okay, in this video, I will analyze the force modeling of a collision, of a real collision that what you see over here in this video. We have two experimental cards. One is yellow labeled, another is red labeled. By the way, the cards has some information that the mass of the left card is given as 705 grams and mass of the right card is 704 grams, almost there. Equal masses, and the movie is like 300 frames per second. Let's check the rating. Yes, that's it. And we're going to start not at this 0th frame but the first frame. All right, so let me run the video first. Well, it's quick because it's very fast. It is 300 per frames per second. If I run it like frame by frame, this is what you see. It's going on. Two experimental cards, they are coming towards each other with some constant velocities, but they collide. And they collide. There are these bumpers, and these bumpers are like foamy material. It bounces back, and it's kind of, it's foamy because it's kind of this collision is a kind of soft. Well, if there will be no any foam material between these cards, the collision will be very hard. But they just put this foamy material so that maybe this is making the collision a little softer. Okay, so that's it. I mean, this is just filmed, and we're going to analyze this video by modeling the force. I mean, it's going to be a dynamical model, so we're going to just guess the force as a function of time on one of the cards. I'll just pick up the left card, so I will just model the motion of the left card. But how I'm going to model it's going to be force modeling. First, I will collect the position data, raw data for the card. Let's do this first, okay? Let's create first. Let me also first enlarge the font so that you can see better. Okay. So okay. Create point mass. I created the point mass, and the mass is over here 0.758 kilograms or 0.706 kilograms. Well, I'm going to collect the x versus time data for the left card. So we're going to model only left card, which has this yellow label. So I'm going to just but first let's show it to you that this is our scale, that these three marks, every mark over here on this is 10 centimeters, so this 3 marks is 0.3 meters anyway. Okay, so this is what I have done, and next is the coordinate system. So we're starting the coordinate, or the origin of the coordinate system as an initial position for the left card. So I just move this into center of the yellow label. Okay, so now let's concentrate on taking this raw data, and for that I'm just going to enlarge it so that I can pick up to the center of the yellow label and push it. So enlarge it so that the tracker can make a difference of this yellow with the surrounding. And then next is we're going to collect the position at every frame for this center of the yellow. Okay, I just first let's choose no trails. Okay, so next. So what I'm doing now, it's and the tracker is picking up the position information for the card at every frame. So see the x versus time graph, it goes like almost a straight line, but now the collision is happening, and obviously the car is not going to the right anymore. It is bouncing back. So this is very clear in this plot. Okay, and we get, okay, so that's it. So we got all the position information, the raw data for the card. So why I'm doing this, because once we just make our model, we're going to just compare the position of the model particle, whether it's matching this raw data or not. Okay, so let's make this invisible now, and then run the video back from the to the initial position. So let's first produce our model. Choose track new and dynamic model, because we're going to model force Cartesian. And okay, this is what you see. This is the model. Let's pick up a different color for the model, because the mass A is also the same color. So model, make it blue. All right. So as soon as we created the model, this model circle, the blue circle, just appears. When you run the video, there is nothing going to happen to the model particle, because everything is zero about this. Let's first the model enter the model's mass. It's 0.7. Sorry, 0. Okay, something wrong. All right, 0.758. And of course, they're going to parameters. And the first thing that, since initially the card starts with a constant velocity, let's pick up a velocity for that. And for this, let me first go to mass A and then switch to Vx. So V starts like around 0.2 meter per second or so. So that means we also produce only one single. Let's produce Vx for the model to be 0.2. Okay, and observe that if you run the video frame by frame, you see now the model particle just follows the card. Okay, but this will continue forever, because even if the card is bounce back after the collision, this model particle will continue its motion, because there is no force over here. So it will keep its constant velocity almost forever. But since during the collision there is this time-dependent force appears, we have to model this force. But what's going to be modeled for the force? Well, obviously, when the card is is experiencing the collision, the force is going to be like increase from some very slow value, because once first touch this foamy end points of the cards, both cards are touching each other. So because of the softness of this material, the force is going to increase slowly, and once these stretched because of the collision, the force will reach its maximum value. And what I'm showing these arrows on the left card, of course, because when the card is just experiencing this collision, the force on the card, on the left card, is going to be toward the left. So at the maximum compression of this foamy material, the force is going to be very large, and after the the card is finished this collision, when these two foamy materials are just separated, the force is going to be zero, but the card is now moving to the left with some constant velocity. So it seems that the force goes like, if T0 is the center of the collision, the time center of the collision, then how the force is increasing its value is going to be like goes zero first, because it doesn't touch, so there's zero force, and then it becomes maximum value, and then it becomes zero again. So this kind of like, if you picture this like this is t-axis, this is force. It goes like maybe roughly this. Because if you just picture very rough picture for the force, it goes like increasing value over a time. It reaches a maximum value when the collision is just, you know, in such a case that these foamy materials are very squished at its maximum position, and then it will drop again because they are leaving each other, they're separated again. So, I mean, the force function we are going to model is just looks like very roughly over time as this kind of expression. But, you know, we expect, of course, this is a smooth transition. So the best function that we can have to mimic this change, analytical function, is going to be a bell-shaped curve like this, okay? But a bell-shaped curve like this is the time axis and this is the force. Bell-shaped curve like this is just a kind of a Gaussian. I mean, what is Gaussian is exponential minus t minus some t0, because this is the center of the collision over time, right? The peak appears at maximum value at t0, and divided by c and take the square of this difference. Well, c, you can view c as the width of this bell shape, okay? Well, for example, for smaller c, this bell shape will look like a narrow, and for larger c, this looks like wider. So that means, you know, you know what's going on over here. This is our first parameter. The t0 is going to be first parameter, of course. The time that the collision happens at its maximum squeezing of the foamy material. And this is the center for the collision over time. The center for the collision is t0. And next is the c parameter that governs the how long the collision will experience. For example, for the materials which are very soft, the collision takes place more time. For hard materials, the collision takes over a shorter time period, right? So I mean, this is going to be a second parameter, the c, whatever the c is, and this is exponential. This is bell-shaped, and also what is going to be maximum value of this force? This constant, this maximum value, is going to be provided by another parameter, which is going to be f0, and it's going to be multiplied by e, because when t is equal to t0, this exponential becomes maximum, having the value of 1 for f. But we have to, of course, play also the maximum amount of force, right? Occurring at the center of the collision. So we put this f0, and we'll also play with f0. So we have three parameters, t0, c, and f0. f0 is the maximum force. Well, you see, after modeling successfully this collision, we will be able to guess what is going to be the maximum force between these two cards, okay, during the collision. This model will let us also determine the maximum value of the force happening between these two cards. Okay, so this is our model. I mean, f0 exponential function t minus t0 divided by c squared. Because, you know, bell-shaped curve has this format. Okay, let's put this over here, fx, because the collision takes place in the x direction. Let me disappear this. Okay, so f0. Let's first put our next parameter, which is t0. T0. All right. And the other parameter is c. The parameter is c, the duration of the collision, and the other parameter is maximum force, f0. Okay, so, and come over here, just type, well, it is going to be a negative force, so that we have to put minus sign over here, f0 multiplied by exponent, open a parenthesis, one more parenthesis, and one more parenthesis. Why I'm doing this? Because I'm just going to t minus t0 over here type, and after closing the parenthesis, divide this by c, okay, and then take the square of everything. Square is just this, and put the minus sign in front of it. So there it is. Okay, this is our let me enlarge it. Yeah, you can see it. Okay, so this is now the model window, and this is a force expression, which is, you know, bell-shaped curve. This is going to produce a bell-shaped curve. Okay, now what is first case about these parameters T0, C, and F0? Let's check first the position information for the raw data. This is for the raw data, that the card is going in the positive x direction first, and then the collision happens over here, then going back. So the collision is happening right somewhere over here, and this corresponds to a time which is around 0.7 or 0.75. So let's put 0.7. You see this when I just put this mouse cursor over here. You see the yellow labels over here, and this shows like t is equal to 0.7 or 7. Let's make it 0.073. 0.073. Okay. All right. So the other thing is, let's also compare this x versus this to the model. So you see the model goes like forever at a constant velocity, because we haven't put this f0 value, and so still the model sees a zero force. That's why it's going over a constant velocity over all the time. But now I'm going to let's discuss also about the duration of the collision. Since a duration of the collision is like between, let's enlarge it a little bit. This is somewhere 0.07, and maybe the collision takes place over this time, this much time, which is about like maybe 0.02 or 0.0. Let's give some number, right? It's 0.03. And next thing is we have to provide f0, and this f0 is, let's say, put 2. Okay, so now you see whenever I put this some non-zero value for the force, you see what happens to the model's data. Model's data is just a little now changed, but you know, this change is not enough because it's not going back. So maybe we should increase this to 4 or maybe 5. You see now, at least for the first part, until starting from the first frame to right here that the collision takes place, almost the model follows now the card, but after the collision it's not going okay, because you know, this blue circle just falls behind the center of the yellow circle. So we have to correct this. I mean, just we need to work it on more. So well, this is this is 5 means 5 newtons of force, right? And so it seems that the order of the maximum force is going to be around 5 newtons or so. At least we got this idea. But this part, let's run this until the end. Okay, so this part is not matching good. So we're going to play with this. Maybe we can reduce this to 2. No, 3 is okay, or maybe 4 is going to be better. But if it's 4, the duration of the collision is taking more time, then this part is going off. Maybe let's keep this by 3, maybe decrease 5, so increase 5 to 5.5 maybe. Now it's getting better, right? You see, this part is getting overlapping more and more now. When it's 5.5, 5.6 maybe. Okay, it's getting better. 5.8. Now almost okay, right? So just run it. Okay, so you see the blue circle is almost exactly follow the center of the yellow label, which is the location of the car. Well, okay, you see now. Okay, of course you can make it better and better. This part, it seems that a little bit you need to working on it. You need to work on it. Well, but for these parameters, almost it's all okay. I mean, that means the collision takes place at the time 0.073, which is quite obvious, right? This is 0.6, 0.06, 0.07. So the peak is just somewhere over here, which is 0.073 or so. Okay, so this is the time when the force gets its maximum value of 5.8 newtons. Okay. Okay, so that's it. I mean, this is done, but what we have used over here, this we model the force as like a bell-shaped curve. But this expression, which is some exponential t minus t0 divided by c squared, is not only a function. This is not the only function that produces a bell-shaped curve. There is also another type of function that produces this bell-shaped curve. And this looks like more like a Gaussian. And I mean, this kind of exponent, some parameter squared, is more like a Gaussian, known as a Gaussian in math. But there is also another kind of function. Let me put it over here. Let me show it on the board. Let's erase this. Okay, I told you that there is another kind of analytical function that is producing this kind of bell-shaped curve for the force, and it's going to be like some parameter c squared or c, divided by c squared plus t minus t0 squared, and some constant over here. Let's put f0 over here, and this is our force function. Let's try this, okay? And this is called Lorentzian. This is called Lorentzian. So instead of exponential function, let's try this, okay? Let me try this. Now, what I'm going to do is, I'm going to erase this model A. Delete it, and create another model. Dynamical model. Okay, and again, let's change its color to blue. Okay, so let's make this on a single plot. And let's play with the font so that you can see it. Okay, so this is another model now. What I'm going to type over here is this new force, okay, which is f0 multiplied by c divided by c squared plus t minus t0 squared. It's called Lorentzian. Let's play with this. I mean, okay, so let's type first this, or let's type first okay, this is going to be mass, and mass is 0.7058, and the first parameter again is t0, is there, the collision center in time. The second parameter is c, and the third parameter, again, we have three parameter f0. Okay, so I'm going to type this expression now into the force function, which is going to be again minus f0 multiplied by c. Let's take this into parentheses, right, and divide this by again, open a parenthesis, c squared plus t minus t0 squared. Okay, that's it. This is our force function, and well, it's taking a different format. That the format that as I told you, is this time again, this expression is going to produce a bell-shaped curve like this, but of course the parameters might be a little different in compared to the case of Gaussian. So this is Lorentzian. Maybe you can check it on Google. So Okay, what next is first, okay, let's play with these parameters now. So t0 again, let's make t0 again the same. No, it's going to be 0.073 and c0 maybe 0.03. Okay, and what about f0? But f0 is over here, is going to play not the maximum force. It's kind of a different thing. So let's play it with this, like maybe again 2. Okay, so you see this is the model, and compare this to again the mass. Okay, so it seems that this force is very large. Let's make it 0.5. No. Okay, so first run this. Okay, so you see is it's large. Let's make it 0.1 maybe. No, still large, 0.02. As I told you that this, in this case, the f0 is not the place the maximum force, but something else, because we have also this product multiplication with c. Let me get rid of this. Okay, so right, all right. So what's well, this comparing these two means that okay, this f0 parameter is large, and let's make it smaller and smaller. Play this. I mean, maybe 0.5. All right. So no. Okay. Oh, we haven't provided the initial velocity. The initial velocity, we forgot it. 0.21 or so. Yeah. Okay, now. Now we have to increase this now. Okay, now it sounds okay. 0.5 is small, 0.8 is, we're getting there. At least until the collision, almost we are overlapping with the raw data. But let's increase this further, like maybe 1.5. Oh, it's large now. Let's make it smaller. Okay, so it's getting there. What about 3? Okay, but I think we have to play also with this, maybe 2. Okay, and what about this? 72? Yes or no? Change a little bit. Okay, let's keep it this value, or maybe more. All right, so this part is a little off. If you just run the video, but now, yeah, it's almost following. It's almost following at every frame. The model is following successfully the car. A little, it's going off right after this point. It is a little going further. The model goes beyond the car. Maybe we can decrease this to maybe 2. No, or 2.5. It's, I think, almost there. All right, so what about this, or this? 35 maybe. Well, okay, anyway, you see, this also works. This also works. This doesn't mean, this shows you that you don't have to, pick up one particular analytical expression first. You can try other expressions. For example, in this video, I just tried 2 force functions. One is Gaussian, one is Lorentzian, and Gaussian I've done. And you just, maybe you can compare the models of Gaussian and Lorentzian. Maybe you can have much better successful overlapping with, let's say, maybe Lorentzian or Gaussian by playing with these. Of course, you have to work on it. You have to play with the parameters more and more. I'm just keeping it short over here to just give you an idea. I will also put this, the file, the tracker file on the UBS page, so you can download it and you can work on it. So, okay, that's it. I mean, you see, we can model even the collisions in tracker by just dynamically and by just playing with an analytical function, an analytical force function. But what gives these functions to you, what this modeling will give you is you can determine the maximum force on at the maximum collision time, right? And this is something that you can only do with modeling, right? So also you can just play with different types of materials between the cards. For example, this foamy material is providing this much collision time, 0.02 seconds. Maybe you can use other materials. Other materials will give you some larger or smaller C value. Well, these C values will be giving you information about the softness of the material that you are using during the collision. So you see, if you just want to characterize how hard or how soft a material is, you can put this material between these two cars which you can collide, and from that, this value will give you some measure of the softness or hardness of the material. So you see over here, this with just the application of some physical principles over here will give you some more information, like maybe what kind of materials are softer, what kinds of materials are harder, etc. These kind of things, This is what the benefits of the modeling is giving you. Bro, I'm sure that there are more other benefits if you just think about it, right? And you can find. So this is one very neat, nice example of how modeling provides you some extra information about a physical process. Okay, that's it, and I'm just stopping here.